So thank you for tuning back in. Today we're going to be talking about one of the most important techniques for this class. If there's one thing that you want to take away from this class, it would be what we're talking about today. I might say that this is the most important thing that we'll learn and one of the most powerful things that we'll talk about in this class. So let's jump into it. And today we're going to be talking about U-Substitution. So, before we jump into U-Substitution, let's take a moment to consider where we're at right now. We've been talking a lot about integrals. And if we remember, integrals are sort of like the opposite of derivatives, where we go backwards from a derivative to the function that we started with. And we've dealt a little bit with indefinite and definite integrals. We know how to we should feel comfortable taking the integral of x to the fourth dx. That's sort of just the power rule. We'll get 1/5 x to the fifth plus c, right? However, if we're going backwards, let's think about what we learned from derivatives. So we learned different techniques like the product rule, the quotient rule, the chain rule, and when we did those to get our derivatives, those final functions were quite complex. So if we're going backwards from a derivative, we're going, this is, let me try to draw it out. So we go from f to f prime, this is the derivative, and then we're going to go back via integration. And we learned that to go from here to here, there's a lot of techniques. Quotient rule and chain rule come to mind. And we remember that this f prime was sometimes very, very complex depending on the technique that we used. Well then, if we're integrating backwards, we start with this. So sometimes we're going to deal with integrating a very complex function, and we can't just rely on the power rule, which is why U-substitution comes in super handy. U-substitution is going to take a whole class of problems with integrals that seem extremely difficult because of how complex they look, but completely simplify it into something much more manageable. Let's jump into it. So, what is U-substitution? I'm sure you're looking at the slide and you're like, what in the world is going on? I do not see any numbers on this slide. And, well, you're 100% correct. There are no numbers. But let's walk through it. And hopefully it'll clear up a little bit of the confusion. But yes, let's just see what happens. So, what is U-substitution? It's a method of integration which is especially useful for functions whose derivative involve the chain rule. So, this is just a basic definition of an integral. I guess it's not basic, but what this is saying is if we take the integral of a function that looks like this, f of g of x times g prime of x dx, we get capital F of g of x plus c. And well, let's test this. So what is the derivative of this term right here? Well, that's going to require the chain rule. We take the derivative of the outside, which gives us lowercase f of x, keep the inside, then multiply by the derivative of the inside. So that's the chain rule right there. And sure enough, that is our integrand right here. So this top line is just telling us the integral of the chain rule. Okay, so that's pretty cool. But still, if we come across something that looks like this looks quite difficult to integrate on our own, even if we do know this fact. Like, figuring out what f and g is could be quite complex. So, we're going to use the technique of U-substitution, which will greatly simplify this problem a lot. So, with U-substitution, we're going to let u equal g of x. Let me just get rid of this here. We're going to let u equal g of x. So u is just some variable. We're going to do a change of variables. So if we let u equal some function of x, we want to make a change of variables in terms of u, so we have to change everything to u. So if we take the derivative of u with respect to x, we get g prime of x. That implies du equals g prime of x dx. I like to go a little bit further and say that dx is equal to du divided by g prime of x. And the reason why is when we go back to this integral, we can now make some substitutions. So this is equal to the integral of f of g of x, which we said is u, so we'll make that substitution, times g prime of x, and then dx we said is this, so we multiply by du times g prime of x, and here we see these g primes, they cancel with each other. These cancel, and then we're left with this, the integral of f of u du. So now we went from this really complex function to a function of one variable, which should be much easier to solve. We're able to handle that for the most part, because that's just the antiderivative of u plus c. But then we would want to make this substitution back in. So this would be f of g of x plus c, which is this right there. So once again, this looks quite complex, but all we're doing is we're introducing a new variable, letting it equal some function of x, then taking this integral, changing the variables to u, and then integrating in terms of u. So still might be a little bit confusing, so that's why I've written up a ton of tips and steps for U-substitution. Hopefully this will clear things up a little bit. So what are the steps? The first step is to choose a good u, and arguably this is the hardest part about U-substitution, because there's so many u's you can choose from. Here, like, we know that if we let u equal g of x, if the function is in this form, then it'll work out pretty nicely, like we just demonstrated that. But it's so hard to tell if, like, I give you x squared times x cubed plus 1, like, sometimes it's hard to tell what is f of x, what is g of x. So knowing what g of x is or what u should be right away can be really difficult. So choosing a good u is the first step. And I said that a good u is basically an expression that appears in the integrand and whose derivative also appears as a multiplicative factor in the integrand. So let's take a look back here. U equals g of x was a really good choice for a u, and we'll check the two criteria. First of all, is it in the integrand? Yes, g of x is right there, so we can make that substitution for u, so that's a good thing. Second, we want to check, is its derivative a multiplicative factor in the integrand? Well, the derivative of g of x is g prime of x, and sure enough, we have g prime of x. It is a multiplicative factor, so that would be a really good choice. And the main reason why we want it to be a multiplicative factor is when we change variables into u, this term will still stay the same, but since it's being multiplied with f of u, when we make the substitution for dx, this g prime of x in the denominator will cancel with that. So that's why we want it as a multiplicative factor. So with that said, some potentially bad u's, not always bad, but most of the time bad, would be like u equals x. Like, sure, we'll see a ton of integrals with x in them, but choosing u equal to x doesn't really make too much sense, because when we compute du dx, we get du dx equals 1. That's the derivative of x, but then we don't really cancel anything, right? That 1 just doesn't cancel with anything, and we're just left with the same integral, so that doesn't really make sense. Similarly, if we let u equal the entire integrand, well then there's nothing left to cancel with, so we don't simplify it anymore. Hopefully it'll make sense once we do some examples. So after we choose our u, we're going to want to compute du dx and solve for dx. So that would be right here. We chose the u, solved for du dx, then solved for dx. Then we're going to substitute the expression we chose for u into the integrand, and also substitute the new expression for dx. So make those substitutions, do those change of variables. Do your cancellations and simplifications as needed. If we're working with a definite integral, we should change the bounds so that way they're in terms of u. This should make sense, right? If we start with an integral whose limits are in relation to x, because we're integrating with respect to x, when we change variables to be in terms of u, our final integral should have limits in terms of u. So we'll have to make that change this change of limits. And we'll touch on that more in a bit, but this is something to keep in the back of your mind and will be very important. Okay, so after we do all of our substitutions and cancellations, there shouldn't be any x's present in the integral. If there are, try to do other substitutions or further cancellations. This is really important, because if we substitute in terms of u, we want to integrate in terms of u. If there's still an x present, what are we supposed to do? How are we supposed to integrate if we have both a u and an x? It just doesn't make sense. So we want to make sure no x's are present. Just a brief aside, if you enjoy calculus and you want to continue learning more about it, I highly recommend taking a multivariable calculus course, where there you will learn how to integrate when multiple variables are present. But that's not this class right now. We're just working with single variables. So do ensure that there are no x's. If there are, either make sure that you've simplified as much as you can, or if not, then try to choose a different u. So finally, you want to integrate in terms of u, then substitute the u expression in, so we're back in terms of x. Remember, u is a variable that we created, but the problem probably gave it to us in terms of x. We want to have our answer in terms of x. And finally, if it was an indefinite integral, tack on your plus c. So the best way to get good at U-substitution is with practice. So that's what we'll do now. I'll walk you through a handful of examples, and yeah, hopefully we will be professionals at U-substitution by the end of it. So this is our first problem, the integral of 2x times x squared plus 1 to the 4th dx. If we think about the techniques that we know already, like the power rule, things like that, that doesn't look like it applies here. Like, it seems quite complex to do it here. So that's not going to work. So here we're going to require U-substitution. I have a little video here which will show us the correct steps of U-substitution. But before that, let's try to solve the problem on our own. Once we come up with the solution, then we'll check it with the video. So let's zoom in here. So the first thing we want to do is choose a u. Well, I mean, you don't have to choose a u. You could, like, take this x squared plus 1 to the 4th and multiply it all out until you have a huge polynomial. Then multiply it by 2 to the x, and then you have the addition of a bunch of terms. But that would be, we know how to integrate that. That would just be a bunch of power rules. But what if this was like to the 7th power, or to the 10th power, or to the 125th power? We don't have that kind of time to multiply that out. So we're going to use U-substitution. So the first step is choosing a good u. So let's just see what would be a good choice for you. Let's try u equal to 2x. So that's the first step, choosing our u. Then we want to find du dx and eventually dx. So this tells us that du dx, we just take the derivative of both sides, equals 2. That tells us du equals 2 dx. And solving for dx, we get dx equals du over 2. So we've chosen a variable and we've solved for dx. Let's try to go back to the original integral and make that substitution. So we have the integral, of 2x, which we said is u, times x squared plus 1 to the 4th, times dx, dx, which we solve for here, so we'll make that substitution, du over 2. Okay, well, we have like this 1/2 term here technically. Let me just write it out a little bit better. Integral of u times x squared plus 1 to the 4th times 1/2 times du, something like this. So we could like bring this constant out, but let's not worry about that now. Let's just take a look at what we have. Does this help us? Is this any easier to integrate? No, it's not. like I still have this x squared plus 1 to the 4th term. I didn't get rid of it. And the only way to get rid of it, well, most of the time, is by cancellation, right? If we go back to the above example, I won't scroll back, but remember how those g primes of x canceled when we did that substitution here. This 2 does not cancel with anything in here, so I can't even integrate this because I still have it in terms of x and I can't simplify it any further. So u equals 2x was not a good choice. All right, let's try again. Let's try in pink. So, okay, 2x didn't work, right? We started with this thingy here. What else could work? Let's try, how about this term here, this x squared plus 1 to the 4th term, because we couldn't get rid of it. How about we just start with that? So u equals x squared plus 1 to the 4th. All right, now we'll take the derivative with respect to x. So that's going to require the chain rule on this side. So 4 times x squared plus 1 cubed times derivative of the inside is 2x. Okay, and then you can solve for dx, and we get this is equal to du over 8x x squared plus 1 cubed. All right, let's go back to our integral. Integral of 2x. Then we have that term, which we chose to be u. So we'll multiply that with u. I just want to use my color. Okay. And then dx, which we solve for right here. So we'll make that substitution as well. Du over 8x x squared plus 1 cubed. And you're like, okay, 2x and 8x, that's a cancellation right there. So this x term and that x term cancels. So we're left with the integral of, well, this is going to be a 2 over 8, so that's 1/4. I'll just bring that 1/4 out front, so 1/4. Then we get u times du over x squared plus 1 cubed. And again, we kind of run into the same problem. Like, I would love to integrate this, but I still have this x term here. I don't know how to get rid of it. I'm like, okay, I can't simplify it any further. I've done as much as I can, so once again, probably chose the wrong u, and sure enough, we did. So this also isn't correct. Okay, so now you're like, okay, what should I choose? It's really hard to choose now. Like, do we do the entire integrand? Probably not, because there won't be anything to cancel with. So sometimes we have to be a little bit creative. Well, let's try u equals x squared plus 1. And I'll take a brief moment to explain why we should think to do x squared plus 1 before we actually do the calculations. Remember, a good u is one who appears in the integrand, and 2, whose derivative appears as a multiplicative factor in the integrand. Let's take a look at what we saw here. U equals 2x. 2x is present, but then the derivative of 2x is 2, and if we, exclude what we chose for u and look at the rest, that 2 doesn't cancel with anything there. Like, it's not good, no good, and that's the problem we ran into. Same thing here, x squared plus 1 to the 4th. It's good that we chose that because sure enough it's in the integrand, but when we take the derivative of it and we get this thingy, that's not a multiplicative factor. All we have is 2x left to cancel with, so that is not a multiplicative factor. It's not a good choice. If we use x squared plus 1, it appears in the integrand, and the derivative of x squared plus 1 is 2x, which is right over there. So hopefully we'll be able to cancel some stuff. Let's try it out. So we want to find the integral of 2x times x squared plus 1 to the 4th dx. So we'll let u equal x squared plus 1. Let me use a different color. Let's see, what color should I use? Blue. U equals x squared plus 1. That barely looks any different, but too bad. Du dx equals 2x. That tells us that dx is equal to du over 2x. All right, so we'll return to our integral. We have the integral of 2x. Now we'll substitute our u in for x plus 1. So I'll use this brighter color. U to the 4th power. And then this dx we solve for right here. So we'll multiply this by du over 2x. And sure enough, this is the derivative of the u that we chose. This was the multiplicative factor that we noticed. So these are going to cancel with each other, which means that we're left with the integral of u to the 4th times du. Hey, we know how to integrate that. That's just the power rule. So that's going to be 1/5 u to the 5th plus c. But remember, our problem was in terms of x. We solved it in terms of u, so we have to make it in terms of x. And all we need to do is we see a u here. We let u equal x squared plus 1. So we're going to take this, plug it back into here, and we should get 1/5 x squared plus 1 to the 5th plus c. And sure enough, that is our answer. And if you take the derivative of this, try it out. Take the derivative of that and see if you get this. Sure enough, you will. This is just a simple chain rule exercise, and it will be identical. So here, x squared plus 1 was our good u. Let's take a look at this video. Yeah. All right, so this is the integral we started with. And we chose u equal x squared plus 1. We took the derivative, solve for du. So we substitute in our u. Then we substitute for dx. So we put du over 2x for dx. Now we're going to cancel our 2x's. And now we're left with a simple integral in terms of u. We'll just use the power rule. Get 1/5 u to the 5th plus c. Then go back in terms of x by substituting what we let u equal to. And that's our answer. All right, so let's get back to where we were. Wonderful. Okay, so let's do a couple more problems. That was just a blank page. All right, how about this? This looks tricky, but we will be able to solve it. So we don't really know how to do this with power rule or anything. That just looks kind of complex. There's also a square root in here, which I don't really like. So let's just make it in terms of a power. So this is equal to 3x squared times x cubed plus 1 to the 1/2 dx. This is a technique that I really encourage you to latch onto if you're comfortable with it. Square roots aren't really nice to like deal with derivatives and integrals because they're just kind of obscure functions. So I always like to change square roots, cube roots to their power form because we know a lot of things about how to deal with derivatives and integrals with powers. We have our rules for those. So this is just a technique that I encourage people follow. So what are some possible u's that we could choose from? Remember, we want it to appear in here, so let's just think like a couple of ideas. We could have like 3x squared. We could have like x cubed plus 1 to the 1/2 power. We could have like x cubed plus 1. So these are just sort of some ideas we could have. Let's take a brief moment to figure out which one of these will be good. So 3x squared, that appears here. Next we check if its derivative is a multiplicative factor. Derivative of this is like 6x, and there's no like x term that's a multiplicative factor. This is still a square root term, so we're still going to have that. It's going to be very icky, so not fun, no good. If we take the derivative of that, well, I don't really want to worry about computing it out all the way, but it'll be the chain rule. This 1/2 will go to a negative 1/2, so there will be a square root in the denominator type thing. So the denominator or the du will still have a square root. So like even if when we substitute in for here, we get rid of one square root, but then when we substitute for dx, we introduce a new square root. So no good there. How about this? X cubed plus 1. That's there. That's good. Derivative of that is like 3x squared. Hey, that's right there. That looks pretty good. So let's try u equals this. Before I continue, just want to make a brief point. The derivative of x cubed plus 1 is 3x squared, which, by the way, this is the correct u to use. You should be using this u. And we said that, okay, 3x squared is the multiplicative factor. If this was 4x squared, 7x squared, 10x squared, it would still be okay. We don't need it to be an exact multiplicative factor. The main thing is like the x term should be similar enough because we want those x terms to cancel. The constant doesn't matter because constants we know we can just take out of integrals just like that. We're chilling. But those x terms are really, really what we care about canceling because we want it to be in terms of u. So let's try it out. Let's let u equal x cubed plus 1. Then we'll take the derivative, du dx equals 3x squared. This tells us du equals 3x squared dx. And we want to solve for dx. So that's 3x squared over du. We'll return to our integral. We get integral of 3x squared times the quantity x cubed plus 1, which we said is u. So that's our u. That is still raised to the 1/2, right? That is still raised to the 1/2. And then we have this dx term here, which we solve for there. So we'll make that substitution as well. Times, sorry, this is incorrect here. This should be du over 3x squared. So with that substitution, du over 3x squared, now we can see those two cancel, which is really great. Those go away. And now we're left with the integral of u to the 1/2 du. And that's just a simple power rule type thing. So we increase the power by 1, so 1/2 plus 1 is 3/2, and we divide by that new power. So dividing by 3/2 is the same thing as multiplying by 2/3. So 2/3 u to the 3/2. Don't forget your plus c. And finally, we want our answer in terms of x. Right now we're in terms of u, so we have to take this and plug it in here. So we get 2/3 x cubed plus 1 to the 3/2 plus c, and that is our answer. So kind of similar to the last example, but still good practice nonetheless. Okay, let's move on where it's, yes, you knew they were coming, and here they are. Trig functions, my favorite, just kidding, not my favorite, not at all. Okay, so, let's start by thinking, like, can we solve this using what we know already? Well, it's not a power rule type question, and this is not the derivative of any function that I know off the top of my head, so we resort to U-Substitution. So let's start by just thinking of some possible u's that we could use. We could use like secant squared because I see it right there. We could use tangent x because that's right next to it. We could also be even a little bit fancy if we wanted to. We can be like secant x times tangent of x. That would leave one secant of x, which is fine. I'm like, okay, well, why don't we just let it be secant x, right? Now it could be pretty much anything in there, right? So those are all potentially good choices. And you can, you could like do some sort of process of elimination, try each one of these and see which one works out best. But I'll kind of spoil it. We're going to use tangent of x, because when we take the derivative of tangent of x, that's secant squared of x, and hey, we got a secant squared right there, so that seems like a good choice. So let's try it out. U equals tangent of x. So du dx, we're trying to solve for dx, that's equal to secant squared x. This tells us that dx is equal to du over secant squared of x. We'll return to our integral, secant squared x times tangent of x. That's going to be equal to u. And then dx is going to be equal to du over secant squared x. Again, we see our terms cancel, which is good. And now we're simply going to be left with the integral of u du. Okay, this one's easy. I can do this. This is 1/2 u squared plus c, power rule, or just something to remember. And then finally, we want to substitute it back in terms of x. So 1/2 tangent of x squared plus c. And that's our answer. So hopefully you're starting to sense a pattern here. Choose your u, solve for dx, do the substitutions, make sure things cancel, and then integrate in terms of u. And that's pretty much all U-substitution is. It's very formulaic, but choosing the correct u is critical. So that way we get a simple equation to integrate with. So yeah, that's another one. Let's try this. Another square root. 25 minus x squared square root times negative 2x dx. Well, this looks kind of similar, to what we did here, where we had a square root term, and we're like, hey, the inside of this, the derivative of that kind of appears outside there. Same thing here. The derivative of that is negative 2x, and that's right there. So why don't we just let u equal the inside of that? So let's let u equal 25 minus x squared. Du equals negative 2x dx. And that tells us that dx is equal to negative du over 2x. And now we'll make our substitution. The integral of the square root of u times negative 2x times negative du over 2x. So this negative 2x and this negative 2x will cancel. And then we're left with the integral of the square root of u du. That's the integral of u to the 1/2 du. We just did this. 2/3 u to the 3/2 plus c. Do your substitution. 2/3 25 minus x squared to the 3/2 plus c. So very similar to that previous question, actually. Basically identical, just the u term was a little bit different. So yeah, we're just getting into the habit of doing this. So hopefully now we're starting to see how choosing u's works and choosing the good u's earlier rather than later. Let's do another one. All right, this one looks tricky now. This one looks weird because we have a fraction, and fractions are not fun to deal with. So, my bed is a little messy. All right, let's start thinking about what our u's could be. Well, remember, we want to take the derivative of a u. So if we let u equal to like x over 1 minus x squared, that's going to require the quotient rule. That's just going to be super messy, and I'm honestly too lazy to do that. Like, if it's so messy, I don't really want to bother canceling things. So that just seems too annoying. Probably not good. So maybe we'll just consider the numerator and denominator individually. If we choose x, well, okay. But then when we take the derivative, we get 1. That doesn't really cancel with anything, so what's the point? If we take the denominator here, well, if we take the entire thing, we'll have to use the chain rule, and all we're really trying to cancel with is this x, so that chain rule seems kind of excessive. So why don't we just take a look at the inside part? Derivative of the inside part is 2x, negative 2x. So that has an x term, and there's an x term right there, so that might be good. Why don't we try it out? I realize I'm talking a lot during it and not writing things out about what makes a good u. But yeah, try to rewind it and listen to me talk about it once again and see if that makes sense. It's really hard to write it all out. I know we take a lot of time, so I apologize for that, but hopefully what I'm saying sort of makes sense. So first, I don't like fractions, so I like to make things not fractions in terms of powers. So this is equal to x times 1 minus x squared to the negative third power. Negative powers aren't very fun either, but I just don't like fractions very much. Okay, we said let's try u equals 1 minus x squared. So then du dx equals negative 2x, and that tells us dx equals du over negative 2x. So let's go back to the integral. We get the integral of x, then we raise something to the negative third power. That something is the u that we chose. And then we make our substitution with dx, so that's du over negative 2x. Okay, we should still be feeling pretty good about ourselves. We have an x here and we have an x here, and those are going to cancel. So that cancels with that. Except now we're left over with this negative 2 term, but we shouldn't be worried about that. That's just a constant. We know how to handle constants. We just need to make sure to maintain that constant. So let's just rewrite this. Integral of u to the negative 1/3 times, well, how about we write negative 1/2 times du. That is the same thing as that, right? Just bringing out that constant. And in fact, let's bring this constant outside of the integral, because we know we can do that. So that's equal to negative 1/2 integral u to the negative 1/3 times du. That will require the power rule. So negative 1/2. Increase the power by 1, so negative 3 plus 1 is negative 2. Divide by that power, so we get 1 over negative 2 times u to the negative 2 power. And then we'll throw in a plus c as well. Can multiply this out, we'll get 1/4 u to the negative 2 plus c. And lastly, we need to make our change of variables back in terms of x. So we'll take this, plug it back in there, and our final answer will be 1/4, 1 minus x squared to the negative 2 plus c. So the main thing about this example was seeing that sometimes the denominator doesn't always cancel fully. That's okay. As long as we get rid of those x terms, that's all that matters. We can handle constants. Those are easy to handle. If we're integrating in terms of u, we shouldn't worry. But if we still have x terms left, that's not good. So that is a very helpful example there. Here we go, one of my favorite questions. Integral of cosine of 8x dx. What? What in the world? How are we supposed to do this? All right, let's think about it. You should not say negative sine of 8x. If you did say that, that's okay. I mean, I understand why you would say that, and it's a perfectly fine answer. The issue is that when we do the derivative of negative sine of 8x, we'll get like cosine of 8x, but then there's still that 8x term that we have to take the derivative of. And some of you will say that, okay, well, if negative sine of 8x doesn't work, because when we take the derivative, this will multiply it by 8, like we'll get cosine of 8x times 8, well then why don't we just say that it's equal to negative 1 over 8 sine of 8x, so that way that 8 cancels with this 1 8. This is actually the correct answer, so good for you. But if that didn't make sense, which I'm sure it didn't, because I didn't really write it out, let's do it with U-Substitution, and it'll be a much better understanding of why we get this answer. It's good if you can come to this directly, but sometimes we have to be careful and make sure we're considering everything going on in the integration. But let's get rid of this, and let's do it with U-Substitution. The good thing about this is that there aren't many choices of u to deal with. Like, we can't really choose cosine of x, because that doesn't appear in here. We have cosine of 8x, but not cosine of x. So that's not a good choice. So really, our choices are like cosine of 8x or 8x. And cosine of 8x, that's like the entire integrand, which we said would probably be a bad u. And then 8x, well, that's in terms of x. We also said that would be a bad u. So you might be like, well, he just lied to me. There's no good u's here. But this is where you have to sometimes just trust your instinct and go for it. So let's try what happens if we let u equal 8x. Well, then du equals 8 times dx. And then dx equals du over 8. So we have a constant, which we're going to cancel with something, but we don't really have anything to cancel with. But that's okay, because then we'll just be left with a constant, and we know we can handle constants, so maybe it's not too bad. Let's see what happens. So this is equal to the integral of cosine of u times, well, dx is equal to du over 8. So let's bring that 1/8 term out in front of the integral. 1/8 integral of cosine of u du. All right, that we know how to integrate. It's just the cosine of one variable. So don't be fearful that it's in terms of u instead of x. This is still the cosine function. It's just a different variable. We still know how to integrate that. And now we just have a constant term in front. So this will be equal to 1/8 times negative sine of u plus c. And then we'll substitute in our u. So this is negative sine of 8x plus c. And sure enough, we get our negative 1/8 sine of 8x plus c. So we chose a bad u, or something that I called bad originally, but it didn't turn out to be that bad. And the main reason for that is because this cosine of 8x wasn't being multiplied by another function of x. If this instead was like x times the cosine of 8x, then we would have some issues, right? Because then when we do the substitution in here, we would have this x term here, and then this x does not cancel with this 8 here, and that would be an issue. But since we don't have that x term, we don't really need to worry about canceling with anything. We just need to worry about simplifying the problem into something more manageable, which is exactly what we did. So this is a good thing to keep in mind. If there's nothing to really cancel with, then choosing something in terms of x is probably a good idea. In fact, probably the best idea if there's nothing to cancel with. So yeah, that is that question. Here we go, spicing it up a little bit. This looks tricky. All right, so sine of 2x times cosine of 2x. Let's think to what we just discussed. We might be tempted to choose 2x because we just did it in an example. If we choose 2x, its derivative will be 2. So then we'll be canceling 2 with something. But there is a multiplication going on here, and both terms are in terms of x. We want to cancel probably one of these, right? Because even if we simplify it to sine of u times cosine of u, we still don't really know how to integrate that super well. So if we can get rid of one of these terms, so that way it's either integral of sine of u or the integral of cosine of u, that we can handle. So 2x won't be a great choice. So probably a good choice would either be sine of 2x or cosine of 2x. Actually, both will work. So let's just choose one of them. Let's choose u equals sine of 2x. Well then, the derivative of u, that's going to require the chain rule. So derivative of the outside is cosine of 2x. Derivative of the inside is 2. We multiply those. This is du dx. So that tells us that dx equals du divided by 2 cosine of 2x. And sure enough, we can see that, okay, there's this cosine of 2x term. Those will probably cancel. So we turn to our integral. We substitute sine of 2x with u. Cosine of 2x remains. Do our substitution of dx. We said that's equal to du over 2 cosine of 2x. Sure enough, these cosine of 2x's will cancel. But we still have this 2 term to deal with, this 1/2 term to deal with. So that's going to be equal to, I'll bring it out to the front, integral of u du. So hopefully these two steps make sense. All we did was cancel these. We're left with u times du over 2. Which is equal to u times 1/2 times du. And this 1/2 just comes out front. So 1/2 times integral of u times du. Okay? this is equal to 1/2 times 1/2 u squared power rule plus c. This is 1/4 u squared plus c. And then we'll substitute in what we chose for u. This is sine of 2x, that quantity squared plus c. Sure enough, that is our answer. So again, kind of similar problems between these two. Cosine of 8x and this, there's some similarities where we're taking cosine of some little bit stranger function of x. But based on what it's multiplied with, we have to choose different types of u's. Cool. Let's see. All right, yeah. Let's discuss definite integrals for a bit, and then we'll probably call it a day. So with definite integrals, we have limits to worry about. So if u equals g of x, so this is just giving, the conditions or whatever of a U-substitution. Then the definite integral, you should remember this term from when we introduced U-substitution. That's equal to the integral of f of u du. So we do our same exact U-substitution that we're used to. Exact same things that we've done, except now we change the limits to u of b and u of a. So that just means if we say like u equals 3x, then we change b to 3b and a to 3a. So we're just plugging in our limits into our function of u. Very, very simple thing. So we're essentially we change the limits by plugging them into our expression for u. This is much simpler than it looks on this page. It's just one extra step to worry about, and it's a very easy step. So let's do it. Okay, so this is our integrand. Don't need to worry about the limits just yet, but first we should choose our u, because this looks like it will require U-substitution. So I encourage you to stop this video if you're watching this recorded and try to solve this for yourself. If you're watching it live, well, I'll give you like a couple of seconds to think about it. Actually, let me get a sip of water and then we'll move on to it. I'll spoil what the u is. So think about what u you think would be appropriate to use. Okay, I will spoil it. The best choice for u would be x squared plus 1. And hopefully with the process of elimination, you were able to get that. So u equals x squared plus 1. Du dx equals 2x. That tells us dx equals du over 2x. So this comes down to the integral. So depending on how this is taught in different schools and different online places, some places like to include intermediate steps, sometimes they don't. I do, and the way I do it is kind of strange, and some teachers don't really like how I do it. They have their own conventions, so you can follow the way I do it, or you should probably follow the way that you are learning it in your school. But if you're just learning this recreationally, it's okay. So, with that said, I always like to show my substitution when I put in the u's, so my integrand is in terms of both u and x, and then I cancel things out. So that means I'm going to leave off the limits for now, because I don't want to specify them if I have two variables. So what I mean by that is like, okay, we keep our x, then we substitute our u here, raise it to the third power, and then dx is equal to du over 2x. This is a step I really like to show, because now I'm going to show how this x term and that x term cancel. But I don't like to include my limits, because those limits are tied to a variable. For example, 0 and 1, these are tied to the variable x. What I could do is I could say from x equals 0 to x equals 1. That would probably be a good thing to do, and maybe I encourage you to do that. But since here we're in like this mixed integral with two different variables, I tend to not specify the limits, but in the next step I will. So what we see here is we have this x and that x. So those are going to cancel. I'm going to bring this 1/2 term out front. So this will be equal to 1/2 integral u cubed du. But now I want to specify my variables. And here I actually always write u equals something and u equals something. What are those somethings? Well, that comes from plugging in these limits, 0 and 1, into here. So u of 0 is equal to 0 squared plus 1, which is equal to 1. And u of 1 equals 1 squared plus 1, which is equal to 2. So for our integrand, or our integral in terms of u, our limits go from 1 to 2. So back here, I like to specify u equals 1 to u equals 2. So now this integral should be pretty easy to integrate with the power rule. So this will be 1/2 1/4 u to the 4th, and we're integrating that from u equals 2 to u equals 1. So now we'll just use the fundamental theorem of calculus. 1/2 1/4, plug in the top limit, and then we subtract what happens when we plug in the bottom limit. Let's compute this out. 1/2 1/4 times 2 to the 4th is 16, minus 1/4 times 1. That's equal to 1/2 times 15 over 4. That's equal to 15 over 8. So let's just briefly recap the main differences between definite integrals and indefinite integrals. Two big differences. First, we go from limits in terms of x to limits in terms of u. Very important that we do that. Second, we integrate and then use our fundamental theorem of calculus to get a numerical value. Those are the only two differences. So we should be feeling pretty comfortable with that. All right, let's do a couple more examples. Here we go. Square root of 3x plus 6 dx, 1 to 10. Power rule doesn't quite work here because this would be equal to the integral from 1 to 10 of 3x plus 6 to the 1/2 dx. You would hope to use the power rule, but when we're doing it on a 3x plus 6, that's kind of weird, so maybe not. But in fact, it kind of does work out here if you're careful about how the chain rule applies, but that's an exercise for a different time. So let's try U-substitution. The good thing is there isn't many u's to choose from, so we'll let u equal 3x plus 6. Some of you might be asking, hey, why don't we just let it be equal to 3x? That's a really, really great question. The reason why we don't let it be 3x is when we do our substitution, we'll be left with the u plus 6 to the 1/2 power. That's not really easier to integrate, is it? Right, we're still left with that plus sign, u plus 6 to the 1/2 power. This is just 3x plus 6 to the 1/2 power. Maybe it's slightly easier to integrate, but we can just let u equal this entire thing, so that way we're left with the u to the 1/2 power, and we're fine with adding in this plus 6, because when we take the derivative, the constant goes to 0. So don't be afraid to add in constants if it helps you simplify the integral. With that said, du dx equals 3, so dx equals du over 3. Okay, let's go back to our integral. I'm going to leave off the limits for now because it's going to be mixed. So we get u to the 1/2 power, dx is equal to du over 3. So in this case, it happens to all be in terms of u. There aren't any x's, but let's just simplify this. So this will be 1/3, I'll pull out here, u to the 1/2 du. And now I would want to specify u going from what to what. So we take our limits here and compute them in terms of this function here. So u of 1 is equal to 3 times 1 plus 6. That's 9. And u of 10 equals 3 times 10 plus 6, which is equal to 36. So let's specify that here, 9 to 36. So 1/3, 9 to 36. u to the 1/2 du. That's going to be a power rule. So this will be increase your power by 1 to get this 3/2, and then divide by that new power. Dividing by 3/2 is the same thing as multiplying by 2/3. And then we're evaluating that from u equal 36 to u equals 9. Okay, so this will be 1/3 times 2/3 of 36 to the 3/2 minus 2/3 of 9 to the 3/2. Okay, that's a little bit ugly, but let's try to do it. 2/3, okay, 36 to the 3/2. Well, 36 to the 1/2 power is the square root of 36, which is 6. And then we want to cube that, so that's equal to 216. Minus 2/3. We'll do the same thing. Square root of 9 is 3. 3 cubed is 27. Okay, so we get that. And this is going to be equal to 1/3 of, oh my. Actually, let's just multiply it all out. We'll distribute that 1/3 in. This is 2/9 of 216 minus 2/9 of 27. That's equal to 48 minus 6, 42. Good. One brief thing that I wanted to mention. Another difference that you may have seen with doing U-substitutions with definite integrals is that once we integrate, we never substitute this 3x term back in here. Now this is where different ways of teaching do different things. I tend to do both. The reason why we don't plug this back into here is because we've made our change of limits to be in terms of u. So we want to evaluate these at our limits in terms of u. If we change it back to x, that's not going to work because we've changed these to be in u. So what some teachers will do is they will ignore doing this change of limits to be in terms of u, keep the integral in terms of u, integrate as normally, then make the substitution back in. So that would be equal to, like 1/3 of 2/3 u to the 3/2. Right? That's like what we get when we integrate. Then we'll substitute the u back in, 3x plus 6 to the 3/2. And then that would get evaluated from our original limits, from x equals 10 to x equals 1. That would get you the same answer. And if you think about it, we're doing the same thing, because this 10 goes in here, and we get a 36. And the only difference between these two equations is that there's this 3x plus 6 here instead of a u, but here u would be 36. So it's the same thing, it's just delaying a step. So either way is okay. I guess I don't really have a preference. So I might do both, but that's just an explanation of why we're doing that. Yeah, this will be our last question. This one, it's a little tricky. So, what can we do here? All right, so what could be some choices for you? Remember, when we're choosing with u's, we kind of want to keep it simple. That's another thing I forgot to mention, because we're taking the the derivative of our u. So if we have a u with a square root term, chances are when we take the derivative, that square root term will still exist, and it's not going to simplify things. So we're kind of left with choosing x or 2x plus 1. Let's choose 2x plus 1. U equals 2x plus 1. du dx equals 2. So dx is equal to du over 2. Returning back to the integral, we get the integral of x times the square root of u times du over 2. That's going to be equal to half times the integral of x times the square root of u times du. And now you're like, okay, well, that's not good. I still have an x term there. And maybe you're thinking, okay, I chose the wrong u. Let's try a different u. Let's try choosing x. And you'll probably run into a similar issue if you let u equal x, the derivative will be equal to 1, and then we'll still be left with that term there. So it's like, okay, that's not good. And once we learn more integration techniques, you might resort to one of those instead. But this problem can still be solved using U-Substitution. We just have to be a little bit clever with how we do things. We have an x term here, but that's not too big of an issue because we have a relationship between u and x. So if we solve this equation for x in terms of u, we can substitute that back in here and get rid of the x. So if u equals 2x plus 1, then u minus 1 equals 2x, and x is equal to u minus 1 over 2. So why don't we plug this back into there? We get 1/2 integral u minus 1 over 2 times, I'll change the square root of u to the 1/2, times du. Now it's all in terms of u. So that's looking a lot better. Let's try to simplify things a little bit. I have this 1/2 term here, so I'll bring that out. So that'll make the outside term 1/4 because they multiply. Then we have u minus 1 times u to the 1/2 du. And then this term can distribute into here. I don't know why that u looks so weird, but let's do that distribution. 1/4 integral u to the 3/2 power minus u to the 1/2 power, and this we can handle using the power rule. So this will be equal to 1/4, 3/2 add 1 is 5/2, divide by 5/2, we get multiplying by 2/5. So 2/5 u to the 5/2 minus 1/2 plus 1 is 3/2, divide by 3/2, same thing as multiplying by 2/3, u to the 3/2, and then we have to tack on a plus c because this is actually an indefinite integral. So we can substitute u in here, but first let's distribute a little bit. So 1/4 times 2/5 is equal to 1/10 u to the 5/2 minus 1/4 times 2/3, that's 1/6 u to the 3/2 plus c, and now we'll make our substitution for u, which we said was 2x plus 1. 2x plus 1 to the 5/2 minus 1/6 2x plus 1 to the 3/2 plus c. That is our answer. So yeah, just take a moment to recognize, we started with that, and this is our answer. So, and the steps we took weren't very, very complex. This step here of substituting with the u minus 1 over 2 required some creativity, but everything else was bad. The actual integration we had to do was pretty simple. It was just a power rule. There was some algebra here, but overall everything we did wasn't tricky per se. So that is why U-Substitution is so powerful. Because before knowing U-Substitution, this would seem nearly impossible to us. But with this simple trick, we can simplify it so much. So, with that said, that's going to conclude our lesson on U-Substitution for today. Hope you enjoyed that.